Analysis. This is me, I'm fat, and this is Andrew Wampak, who's less fat. Later, when Andrew Wampak hits me, since I have a lot of mass, he bounces off. What does this mean? This means that more mass equals more inertia. In this situation, this is me, and I'm running at Andrew Wampak. Later, when I reach Wampak, since Wampak has significantly less mass than me, and I have more inertia, Andrew Wampak is sent sprawling. Again, this means that more mass equals more inertia. Force equals mass times acceleration. Here's me, and here's a piece of candy being thrown at me. Assuming that the candy has an acceleration of 1.00 meters per second squared towards me. Since the mass of the candy is very small, the force exerted by the candy is also very small. Here's me again, but this time I'm getting a rock thrown at me. Assuming that the acceleration of the rock is the same as the acceleration of the piece of candy, since the mass of the rock is large, the force exerted by it is also very large. This tells us that force is proportional to both mass and acceleration. This is Little Timmy. Little Timmy has no reaction forces in his world. This is Johnny. Johnny lives in the real world. This is Timmy. This is Timmy's feet. Timmy has no reaction pair forces on his feet. The only force on his feet is the force of the foot on the ground. As a result, Timmy tries to move, but stays only in one place, and becomes very, very sad. Johnny, on the other hand, lives in the real world. His feet have action-reaction pair forces. One of his foot against the ground, and one of his ground against his foot. As a result, Johnny can move and walk like average, normal people. The plank. This is Johnny. Here's the free body diagram of Johnny planking. There is the force due to gravity, and then the reaction force of the gravity force, the normal force. Since force due to gravity is equal to the normal force, F net equals 0. This is Timmy hanging off a branch. And here's the free body diagram where these are the arms. There's a tension force upwards of Timmy on the branch, and there's also a tension force downwards of the branch on Timmy. There's also a force due to gravity which is equal to the force of tension, making F net equal to 0. The ball. Before, we see Timmy running into the wall with the ball. There's a force of the person, there's a force of Timmy on the wall, and there's also a force of the wall on Timmy. Since the wall is immovable, the result is that Timmy gets sprawling backwards from that force, and he's very, very sad as he lies on the ground. Here's the free body diagram of the situation. We have force of gravity on Johnny. The force applied by Timmy is the force normal on Johnny. The force of the book on John, and the force of kinetic friction. On the book we have the force of kinetic friction, force of gravity, force of John on the book, and normal force. We're going to split the force applied. We will set mu k equal to 0.250. Here's mass of Johnny, and here's mass of the book. Here's force applied, which we will set to 215.0 newtons, and the theta value we will set to 41.0 degrees. The mass of Johnny is 50.0 kilograms, and the mass of the book is 10.0 kilograms. We will split up the problems into two parts, lead-up problems and third law problems. Lead-up problem A. Find the x and y components of the force applied. B. Find the acceleration of the system. C. Find the net force on the textbook. The law problem number 1. Find the normal force on Johnny. Number 2. Find the tension force between Johnny and the book. A. Find the x and y components of force applied. F app x equals cos theta times F app, which equals cos 41.0 times 215.0 newtons, which equals 162.26 newtons. Force applied y equals sine theta times force applied, which equals about 141.05 newtons in the upward direction. Third law problem number 1. Find the normal force acting on Johnny. The normal force is equal to the magnitude of the force of gravity minus the magnitude of the force applied in the y direction. This value is equal to about 349.45 newtons in the upward direction. Part B. Find the acceleration of the system. The net force is equal to the applied force in the x direction, plus the force of kinetic friction on Johnny, plus the force of kinetic friction on the book. This turns out to be 162.26 newtons minus 122.635 newtons minus 24.525 newtons, which comes out to being by about 15.11 newtons in the leftward direction. Knowing Fnet, we can find acceleration by dividing Fnet by the mass of the system. This comes out to being around 0.252 meters per second squared in the left direction. Therefore, acceleration of the system is 0.252 meters per second squared in the left direction. Part B of the lead-up problems. Find the net force on the book. Knowing acceleration, we can find the net force on the book by using acceleration times the mass of the book. This comes out to being around 2.52 newtons left. Part 2 of the third law problems. Find tension in the rope. The tension in the rope is equal to the force of John on the book, which is equal to Fnet of the book minus the force of kinetic friction of the book, which equals 2.52 newtons minus negative 24.525 newtons, which equals about 27.0 newtons.